basically, I kept the title of my lecture as Deep Learning and Explainable AI for Malware Visualization. So, this talk would be a collection of work that I have been doing with my students over the years. So, especially one of the recent work that I did with Matteo Brozolo. I will give some glimpse of the work which is basically using static analysis and malware visualization and explainability, which appeared recently in GISA. And this work we did like 1 year back. Like last 2 years, I was uh, pursuing my Marie Curie fellowship at University of Padua. So I had an opportunity to supervise this student, and along with that, we had published one systematization of knowledge paper on visualization-based malware detection in the 19th International Conference ARIES in University of Vienna. Then we wrote an extended large literature review, which is now like available in archive, but it is under review in neurocomputing. I think security through the eyes of AI, how visualization is shaping malware detection, and also some glimpses of work that I did with a master student in TU Delft. I was supervising his thesis, Shubham Kandhar, which is a few shot malware classification approach for family recognition on computers and security, and also a collection of work from group of bachelor's and master's student, as well as collaborator Professor Aaron Visaggio from University of Sanyo, who is a leading malware researcher on computers and security. So I saw that over these days we were given a lot of experience in the domain of malware detection, particularly like static analysis, Windows, Android, on dynamic analysis, and so on. So I would take you to a domain which have been uh, particularly of interest to many companies, especially CrowdStrike is working on malware visualization in order to find out special patterns that the malicious payload carry. So just to build the tone of the lecture, I would be quite fast in couple of slides because these are something that has been known to us since past 6 days. So basically, if we want to understand malware, it is essentially a composition of two words. First is mal, which represent maliciousness, and where could be basically malicious software or hardware. So we are largely talking about malicious software. So any combination of instructions that is written by the adversary in order to victimize or compromise any asset owned by an organization in order to exfiltrate vital information from the organization or a system is called as malware. So a collection of any suspicious software primarily written by an adversary can be thought of as a malicious program, or the umbrella term is malware, which can be used in order to refer to adware, launcher, backdoor, spyware, ransomware, worm, etc., that you can see in this particular slide. So something really interesting to look at is the virus total report. I think all of us might be aware about virus total and how we scan the samples over the virus total. To briefly speak about virus total, it's an online service which encompasses almost 60 antivirus engine running in the background. So as a user, we can actually subscribe to the private API or a public API, and then maybe try to scan the samples over virus total in order to flag whether a given sample is malicious or not. So if you look at the 7 days statistics of the samples that are submitted to the virus total, so we find that the large population of the samples that are submitted falls under the portable executable file format, followed by Android, DLL, and so on. And this is because the whole idea of the attacker is to to look at something that is some technology that is more popular. So in this case, like the Windows operating system is largely used across the organizations as well as the users. So the attackers, they will try to find out the vulnerabilities that are associated with the operating system and the utility that is installed in the operating system. So our focus will be also on a portable executable, even though we have completed some work in our lab on Android as well as the Linux malware, which is the ELF file. So, so what essentially is malware analysis? So malware analysis is a process of dissecting a malware. So essentially it means it's a process of performing an autopsy on the malware in order to understand how the malware works, what is the functionality of the malware, what is the origin, and what impact it can create once it is installed on a victim machine. So largely, we have two types of analysis that could be performed on a given malicious program. So one is called as a static analysis, which essentially means like to perform the analysis without executing the malware sample. We look at different parts of the executable, like we look at the header of the executable file, or we look at the important regions of the executable file, like different sections, or we can look at the disassembled code of the file. We can make the control flow graph of the file, and then we try to prepare the analysis. So static analysis is relatively fast, but the problem that appears with the static analysis is, since it is not the we are not executing the malware. So sometimes if the section a part of the code or a payload is compressed or encrypted, so sometimes the static analysis will fail. So this is one of the initial way in which we try to do an analysis. On the contrary, we have another technique which is called as dynamic analysis, wherein we force the malware to run in the sandbox environment, assuming that the malware will not understand the sandbox environment, and we look at different artifacts pertaining to the environment in where this malware is executing. For example, the registry, the files that the malware has dropped are in different directories. We look at the memory and so on. So static analysis is basically a fine-grained analysis of a given malware, but the problem of static analysis is like we don't know when we need to stop, because if we have to analyze a malware sample, we have to do a detailed control flow exploration of the sample, which might be cumbersome and it is time intensive. So we have another class of analysis where we do both. So we do static as well as dynamic together, and it is called as hybrid analysis. So, having said this, why there is a prominence of machine learning models for malware detection? So, we know that machine learning have evolved at an increased pace, and it has been used in different tasks, especially for solving computer vision and natural language processing. And we have seen that machine learning also has given an tremendous performance on the task related to computer vision and NLP, especially in terms of increased accuracy or performance and as well as scalability. And another important thing why machine learning models or deep learning models have been largely used and is being used today on malware detection and analysis is because of the availability of increased label feed. So for example, we assume basically the samples that are available in the repositories like Virus Share or VX7 or Contagio Mobile or Malware Bazaar. So these are labeled appropriately, and there is huge amount of samples available. So when we have a labeled data available with us, it is relatively convenient for us to make a deep learning or machine learning model which can learn intrinsic properties of the variants within the family of malware for future classification. And also another thing that we have been observing over years is that the computational power of the systems are increasing, especially the hardware cost is like is becoming less. So also the so what happens is like it is easy or convenient for us to basically build a training model. So the training time is also decreasing. So, having said this, even if machine learning models have been used predominantly for malware detection, and malware detection now is becoming a crowded research domain. People are looking at new research problems in malware detection domain. Especially the problems with the machine learning models is like one has to manually craft the features. So as I said, we can look at the features that are related to the header files. We can look at certain byte patterns. We can look at certain opcode pattern. We can look at like control flow graph and so on. So these machine learning models have to be trained on features that are relevant, and this relevance is largely decided by different feature selection algorithms or dimensionality reduction algorithm. The problem is like the feature engineering and feature extraction basically takes time. So thanks to the deep learning architectures which have been evolving over the years, which have got the functionality of automatically extracting the features. So malware researchers specifically have been using different deep learning algorithms in order to build a model which could identify the unknown malware samples. But there are definitely some problems associated also with using deep learning model. Like if we use deep learning model as a black box, we don't know what features deep learning models are using, which can be tweaked by the adversary in order to pass detection. So, so this is a general taxonomy of different types of features that we can extract from a given portable executable or any malware file. So the features can be largely divided into two categories. One is the static features and another is the dynamic feature. In case of the static feature, preliminary analysis is always done in order using printing these strings. So you can use the strings utility. Basically, there is a collection of utility under sys internal developed by Mark Resenwick, which we can install in Windows of OS, and we can use the strings in order to find for the presence of printable strings. So, for example, whether the author name is written or some IP address or some URL is hard coded, which doesn't happen now, but in the older malware versions, also we can try to use the raw bytes, and then from the raw bytes we can decide on some collection, some window size to extract the consecutive patterns from the window by sliding the window slowly throughout the malware to extract n-grams. So n-grams is essentially collection of n bytes in a sliding window fashion, or we could disassemble the malware through certain disassemblers like the linear sweep disassembler obj dump, or recursive sweep disassembler like IDA Pro, Gidra, or Radar 2, and extract the opcode and train the model using opcode or opcode ngram, or look at the hard-coded API call, see the API call function, or we can try to find out the entropy from a given block of code, or we take an executable and represent it in the form of an image. This is what I would be talking today about, and maybe like making functional call graph and control call graph. On the other side, when we are executing the samples in the dynamic in the sandbox environment, we can look at the memory artifacts. So especially if we are trying to use perform analysis on Windows operating system, we can actually install volatility and try to understand the memory artifacts. Or if we want to analyze Linux malware, the ELF malware, especially we can use the Limon as a forensics tool in order to find out the memory artifact, look at the register usage, look at the instructions that have been invoked when the sample is executing, or maybe analyze the traffic of the malware of a system where the malware is installed, like the traffic that is flowing out of the machine and the traffic that is coming inside that machine, using certain tools like Wireshark or T-Shark to find out the malicious artifact. Or we can also look at the API call traces. So these are the important features that we can use in order to build a malware detector. So, as I said, my lecture will be largely today, I would be speaking on malware visualization. So, in malware visualization, what is our interest is to take a portable executable file and represent it in the form of an image. The seminal work on malware visualization dates back to year 2011 by the group of Lakshman Natarajan et al. From Vision Lab, and this is an interesting paper to read and start with, which says malware images visualization and automatic classification. So this is a link from where we can actually look at the data set that they have been using, and some code snippet. So why malware visualization, and what is done in malware visualization? So in malware visualization, we take an executable and represent the executable in the form of a binary. And then what we try to do, once the executable is represented in the form of a binary, it has to be converted into a fixed size image of some amount, some width and height. So let's say a square image of size m cross m, or it need not be square, it can have variable width and height. And why image? The advantage of representing an executable as an image, which have been concluded by many researchers over the year, is that the images basically can capture small changes in the pixel, yet they retain the global structure of the file. So one of the advantage of malware visualization is like there is no need of disassembling or let's say execution. One can start with the raw byte pattern, and using the raw byte pattern, we can have different representations of images. I would speak about few representation, and maybe if you are interested, you can go back to one of the papers that we have written where there are multiple input representation of a given executable. So the advantage of malware visualization is like if let's say we have a malware file which is packed, we can look at a specific, we can create the packer signature by just looking at the image patterns or the texture of an image. and it has been proved also to be resilient to the obfuscation, because the deep learning models, they basically concentrate on a specific region in order to understand whether a piece of code is obfuscated or not. So, uh, in general, what is done in malware visualization is you start with a portable executable file, and we represent the portable executable file in the form of a binary, and then we read 1 byte, and why 1 byte? Because like 1 byte comprises of 8 bit, so 2 raised to the power of 8 is equals to 256. That means every 8 bit can be represented as a pixel, and then we try to plot a pixel corresponding to every 8 bit, and assume that we get an image something like this with predetermined width and height. And we can look at this particular output file, like when we take some generic malware file and we print it, we see some pattern. And why it is very important in terms of visualization is like there is a notion of a family, and by definition family means a collection of variants within the family. They inherit properties from their parents, and they keep on specializing. So if variants of a family A, the variants of a family A will have certain intrinsic properties or byte pattern, which will be definitely different from variants of family B. So what is the interest of the malware researchers is to basically use certain classifier or algorithm that tries to look at the generic patterns that are preserved within the variants of specific family. So which means that if I get a new malware sample which has a pattern something like this on the top part of a variant, we can essentially say that it will belong to the same family to which this particular malware variant is belonging to. So, to motivate further, we can also see three different variants which have been plotted on the top part of this slide, which is basically belonging to the fake Rian malware family, which is a rogue antivirus. So we can see that even though three variants are distinct, because if we see the changes in the line, but there is something that is in the rear part or the lower bottom part of these three images which is constant. And if the classifier is focusing on these three, this bottom part, it can try to classify any novel malware which also has this pattern to belong to fake Rian. Likewise, if you look at the bottom part of the slide, where we are showing three different malware files with different height, we can observe that there are certain patterns that are common. For example, in the top, you can see there is a pattern which is also there in all the three malware files, but of varying width. Also, at the penultimate part of this file, like last but few bytes, you can see that there are certain patterns that are similar. Also, in the lower bottom, uh, there is a byte, there is a string that is common. So this essentially happens because malware writers, they don't spend enough time in writing the code from scratch. What they do is like they borrow the existing code and they keep on specializing. So when they borrow certain part of a code from existing malware, so that becomes a pattern which is preserved across subsequent families. So why this? Because malware writing is also a profit-making business. So the attackers, they cannot wait months or years in order to write a new code and deploy it, because before deploying there is a test phase. This malware authors they have to perform in order to deceive the given malware from the antivirus. So it has been found that there is a reuse of code from old malware binaries. So that is why there are also studies where the malware signatures are increasing exponentially, but they are heavily depending on code reuse. So, what are the different types of images that we can create? So, to start with the basic one, so we have something called as a grayscale. So, on the left side is the hex dump, where the first column is essentially the address, and then from here is the basically the header as well as the bytes of a given malware file. So what we can do is we can actually convert this hex string in the form of a grayscale image, and this can be done using different technique. Either we can use a predefined color map, and based on the color map we can create an image, or just convert every hex byte into basically a pixel, and just keep on plotting the pixel, which is also called as line by line plot. So, so what can be done, assuming that this is a color map? So this is a color map that we can see, which is a 256 cross 256 color map. The reason being that we can never have more than 256 different values for a given pixel. So, so if we are trying to create a color map with the co-occurrence of the pixel, for example, how many number of times zero uh, uh, will will precede a zero, or how many number of times zero will precede one, how many number of time pixel zero will precede two, and so on. And inside this basically we basically uh, write the probability values, like how many number of times they will appear. And how this can be converted into an image is like we start with the portable executable, and we convert the portable executable uh, hex code in the form of a long string of values which are between 0 and 255. And then we take every pair of the values, and the first value is used to index the row, and the second value is used to index the column in the color map, and whatever is the value that is appearing in the intersection of 0 and 1 is basically the pixel. So this is one of the approach that people have been using. So then what we do, then we take the next two pair of the values, in which the first value is used to index the row, and the second value is used to index the column, and at the intersection we get some value which I have represented by P511, some random value over here, which corresponds to the pixel. So so then once we do this, we will get a grayscale image. So another representation is like you start with the raw hex file, and then we use a sort of a color map, and then we can convert the raw hex file in the form of an RGB image. So let's say if there is an color map, how we will do it. So we start with an executable, and this executable is represented in the form of a 1D vector consisting of values, collection of values which are between 0 to 255. And then we will be having three color maps, one for the red, another for basically green, and another for blue. And inside these color maps there are values which are written between 0 to 255. So what we try to do is we again take the pair of values. The first value is essentially used in order to index the row of all these three color maps. So over here 0, and then the second value 1 is used to index the column of all these three color map. So from the intersection of row and column, from each color map, we will get an individual value. And these individual value corresponds to three different values that we have abstracted out of these three planes. So which corresponds to 1 pixel in the RGB. So in this way, what we can do is we can create essentially an RGB image. So then the next type of an image that we can create is also called as an entropy graph image, which looks like a line graph, something like this. So over here we can see it's the byte, and on the y-axis it is the Shannon's entropy, and this line that we can see is the entropy value for a block of a segment. And this particular image is actually used in order to represent a specific variant of a file. So how we do it, we start with the malware file. So over here, let us assume that the malware file is having 2500 bytes, and this is basically divided into multiple chunks. So if we assume that one chunk size is basically comprising of 128 byte, it could be more than that because the chunk size itself is a hyperparameter over here. So we have the first block consisting of essentially 128 byte, and in this 128 byte block we would look at the entropy of all pixel value, which is between 0 to 255, and then we try to find out the average entropy of this particular block. Let us assume it is like 5.1, which is plotted as one of the dot in the y-axis. So likewise, what we try to do is we will try to find out until the last block, and if the last block doesn't contain 128 byte, we add it with some number of zeros and we calculate the Shannon's entropy. So as you look here, imagine if there are 20 blocks, so we will find out 20 different points on this graph, and this particular graph, which is an entropy graph, is used in order to represent a malware file. So this is why this is important and why it is interesting. I am showing some variants of Win32 Switzer, so which is like here variant 1, variant 2, and variant 3, and we plotted in our experiment the entropy graph. So you can look here that the initial 500 blocks are more or less having identical pattern, and also there is some pattern which is over here between 1000 to 1020, which also 250, which also appears in all these three variants. Likewise, if we look at another family, which is Win32 Eluron, and three malware variants, for the sake of explanation, we can see that there is a pattern which is mostly common to all these three variants, but the width will be different because every malware essentially specializes when a variant is created. So we have another class of image that can be created, which is called as the first order Markov. So we start with the one-dimensional vector of a given malware file, which is a collection of strings which is between 0 to 255. Essentially, what we try to do is we are interested in looking at the co-occurrence of two pixels pi and pj. So which means we want to find out how many number of times pi precedes pj. So first what we try to do, we try to take all combinations of byte pattern which are shown here, or pixel pattern which are shown here, which is like 0, 1, 1, 0, 0, 255, which has been borrowed from the upper part of this image, and then we prepare a transition probability matrix. So since we have 255 pixels, so we will prepare a probability matrix of size 256 cross 256, where 00 will contain the probability in which the first pixel 0 precedes the pixel in the column, which over here is 0. Likewise, P01 represents the probability that this pixel 0 will precede pixel number 1, because our interest is the first order Markov, and then we will convert them into the pixel by multiplying the probability value with 255 and either upper ceiling it or finding out the floor function and representing them in the form of an image. So if you can see that there are certain white dots in this given image, and this way of creating an image is called as a Markov image. Then once an image is extracted, we can do some techniques in order to extract different textures that are preserved within the given image. So as I said, like there is some generic pattern that is always inherited by the variants of the given malware file. So our interest is to go back to the image processing techniques and to find out the textures. So essentially what we are trying to do is we are trying to find out whether there are some preserved blocks which have got some spatial intensity arrangements, or whether there are certain color intensities that are preserved throughout the image. So essentially our interest is to monitor visual textures, which basically contains repeated pattern. And for that we can use different technique. One of the classical techniques that have been used is called as the Gabor filter, which is essentially a band pass filter. And Gabor filter basically tries to filter out the frequency band from a given image, which follows between a specific limit. Let's say the limit is L1 and L2. So what it tries to do, if we have multiple Gabor filter, it will try to each filter is basically a different band. So it will try to essentially create new images which will retain the frequency within that particular band. So what we have also done, and which have been reported, is we can create different types of filter banks. And when we use these filter bank and pass the image through the filter bank, we will get different representations of a given image, which will extract different textures, and these textures can be basically used in order to train the given deep learning algorithms. So this is the mathematical formulation of the Gabor filter. I don't want you all to be intimidated with this equation, but what we have to understand is in this Gabor filter there is a kernel of a fixed size, which is represented by k x comma y, and this Gabor filter can be actually focused on a given image, malware image, at a particular angle. So how then we try to design a classification module for classifying a given malware into their respective family, or a malware detection problem wherein a given file is either classified as malicious or benign. So we start with a collection of executable, and from this collection of executable, these executable are passed through a hex tool, which will convert a given file into the raw bytes. And using this raw bytes, we can create a grayscale image, or an entropy graph image, or an RGB image, or a Markov image. Then we can decide on some filter banks, and each filter banks will work on a range of frequency. So here we are having 3 filter bank, so which means that when we try to pass this image through the filter, we get 3 representations, because we are having 3 different filters. So we are having three different representation of a given malware file, and using this we will try to develop a model, and we will try to fine tune this model so that it generalizes to unseen sample, and then we will take the test executable and unseen executable. We repeat the same process. We try to generate the filtered image, and then we try to submit this particular sample on the refined model that has been deployed for prediction during the inference phase. So another technique of extracting the features is by using something called as the LBP, which is basically called as the local binary pattern. And this essentially tries to label every pixel based on a thresholding operator. So what we and this thresholding is done by looking at the neighboring pixel of a given pixel under reference. So every malware file and benign file in the process of malware detection is converted in the form of an image. So image is nothing but a collection of pixels in a range of 0 to 25. And then we consider every pixel. So let us say we consider one pixel and we name it as a central pixel. And we look at some neighborhood around this pixel, and then this central pixel is considered as a threshold. And then what we try to do is we try to set the neighborhood values either as 1 or 0. So if the neighborhood pixel has a value greater than the threshold value, that is the central pixel value, we will convert the neighborhood pixel as 1. On the contrary, if the pixel has got a smaller value than the central pixel, which is assumed to be a threshold, we will write it as 0. And then we read the neighborhood pixel value either in the clockwise direction or an anti-clockwise direction, because it is a collection of zeros and 1, and then represent that collection as of zeros and 1 as a number which is between 0 to 255, which becomes the central pixel value. So let us try to understand quickly what I have been saying. Now, let's say that we have a 3x3 image, a given malware image, which is containing this pixel values like 200, 50, 50, 50, 90, 100 until 210, where the central pixel is 90, which is taken as the threshold. So what is our interest? All neighboring pixels which are having values greater than 90 will be represented as 1, and all pixels which are having values lesser than 90s will be represented as 0. So if you look at the first pixel over here, 200 is having a value greater than 90. So we write here 1, and all other values like 50, 50 and 70, which are lesser than 0, lesser than 90, is written as 0. And then we read this in like 100111010, and then we convert this particular value into a decimal number, which is replaced by the center pixel value. And this we can do for all pixels in a given image. So what are the hyperparameters for this? The hyperparameter is something called as the radius. So from a center pixel, you can think about whether the neighborhood is like 2 pixel away or 1 pixel away, as shown in figure B, or like 2 pixel away in C and D, or the number of neighboring pixel that we have to consider. So for example, in the subfigure A, we are considering 8 pixel. Okay. So in subfigure B, the radius is 1 and we are considering 8 pixel. Subfigure C, we are considering 12 pixel around the center pixel, but at radius number with radius 2. So for the same input, we can have different image representations which can be used for training purpose. And then we also have another famous technique which is called as the gray level co-occurrence matrix. And this gray level co-occurrence matrix also is used uh, to extract the textual information from the image, and it gives the overall spatial relationship between the gray level of the images. So we need to first of all define what is the gray level. So the GLCM has three important parameters. One is the definition of the gray level, the distance, and the angular relationship between the gray level. So let me try to briefly explain what all these three parameters means. So let us assume that we have an image, and we have defined for an image gray level 4, which means like we will have four values like 0, 1, 2, and 3. Then what we try to do is the original image, which has a pixel value between 0 to 255, will now be mapped into these four bins. So some pixel will be mapped to 0, some pixel will be mapped to 1, so and so on. Some pixel groups will be mapped to, let's say, 3. So maybe like everything that is between 0 to 50 will map to 0, 50 to 100 will be mapped to, let us say, 1, then 100 to 150 or 200 is mapped to 2, and the remaining one mapped to 4. So this is just an example to explain that we are having a 5 cross 5 image, where malware image, where the pixel are mapped to 4 gray levels. Then what is our interest is to try to find out the co-occurrence of the pixel. So that means how many number of times 0, 0 appears together, 0, 1 occur together, 1, 2 occur together, and so on. So we actually try to prepare a co-occurrence matrix. So in our case, it will be a 4 cross 4 co-occurrence matrix, where our interest is to look at the number of times 0 and 0 occurs together, which is represented over here by an element 0, 0. 0 and 1 occur together, which is represented by an element 0, 1, and so on. Then we also look at the relationship of one pixel corresponding to different neighborhood orientation. So this is also an hyperparameter. So we can look for pixel that is closer to it at an angle 0, 45, 90, or 135. Okay, so just to give you an example, let's imagine that we have a image which is transformed into a four gray level, and this is the co-occurrence matrix. So let us imagine, like, if the theta is 0, so what and if I want to find out the number of times 0 and 0 is co-occurring, so we are interested to look at the horizontal direction, like in the given image. So in the first row we don't have 0 followed by 0, but in the second row we have 0 followed by 0. So if we move from left to right, so the count is 1, as well as if we take right to left, the count is 1. So 1 plus 1 is 2. So we write over here 2. So likewise, if we consider, let's say, if we want to find out how many number of times 2 and 3 co-occur, so we will look at the original image. So here we have 2 and 3. So 1, 2, 3, 4, 5. Then we can also look at from right to left. So 2 and 3, which is shown in for our reference in red color. So we will be having here 7. So what we try to do is, for a image that is transformed into gray levels, we can have different representations of a given malware variant at different angle, like 45. So if I say 45, so our interest would be to look at 0, 0 at 45 degree, or 90 degree, or 135 degree. So that means for one particular image, what we are trying to do, we are looking at the spatial arrangement of the different hex representation at different angle, in order to find whether our classifier could learn something interesting or not. So from each of this given image, we can extract different statistical features. So if you are interested, you can look at the SKI image library, where the statistical features are basically the contrast, angular, standard moment, where the formula is given until the correlation. So these are sometimes also called as the Harlick features. So essentially, we have 8 different features. So which means that every image corresponding to a given malware can be represented by a vector of size A for a given angle. So if we are considering 4 different angles, so which means that we will be having basically 32 different collections of the features, which you can give it to a classifier. So we start with a given executable. We can represent the executable in the form of an image. Then we can prepare a GLCM matrix and of at angle 0, 45, 90 or 135, and we basically extract from each GLCM matrix 8 different features. So basically one malware file will be now represented as like a size of 32 different vector, and then we label a given file as malware if it is if as 1 if it is malware, or 0 it is benign, and then we will train a given classifier. So we trained a very simple random forest classifier in order to find whether it could be classified appropriately or not. And we actually compared our results with one of the work which was published by Daniel Gibbert in Journal of Computer Virology, and we found that our results are like closer to the work that they did, or in fact better in some cases on other evaluation matrices like precision, recall, accuracy, or F measure. So then to move further, as I said, like we also did one work on malware detection employed by visualization and deep neural network, which appeared in computers and security. So essentially what we tried doing is we solved 2 problems: malware detection problem, where the interest was to identify malware versus benign, and secondly malware visualization, where a given malware uh, was identified into the respective family. So having explained everything until now, so we start with the collection of malware and benign files, and then we convert them into binary, and after converting them into binary, we could represent a given malware file as a grayscale image or an RGB image or a Markov image. So in this work, we we extracted 3 different modalities of a given malware file, and then we used the convolution neural network, which has a prominence on image classification and object recognition problem, which the responsibility of convolution neural network is to basically extract features, and once the features are extracted, these features were flattened, which were then given to the decision layer, which is a composition of multiple dense neural network. And in the case of classification, it gives either malware or benign, and in the multi-class, it will be the respective malware families. So to quickly do a one-on-one on what actually is a convolution neural network, most of us is aware about it, but still for somebody who is new, so we take a given image, and this image is basically convolved through a convolution operator, which will try to extract different types of features from the given image. And then this is carried forward by the max pool, which basically takes the maximum information from this feature, and then again from the subsampled image that we get from the max pool, we again use the convolution operator, uh, perform the extract feature, perform feature extraction, and then again we perform max pool. So we can have as many number of times this convolution and max pool repeated based on the architecture that we are trying to devise. And once we have converged on the number of convolution max pool, the output matrix is converted into a linear vector through the flatten operation, and it is given to the fully connected network, which will basically eventually identify a particular label, which will predict the label for a given input like cat or dog. So the convolution neural network essentially has three important property. So the first property on which the convolution operation is focused on is property number one, which says that some patterns are basically smaller, or interesting patterns are smaller as compared to the whole image. So for example, if I take a picture of a bird which is sitting just near to my table, we see in the picture the beak is basically closer and it is more emphasized in the image. On the contrary, if the bird is sitting on a tree, and if I take the picture, I also get the background of the bird, which is like a tree. And if I want to try to do a classification of the bird based on the beak, basically in the first image the beak is enhanced, and on the second image the beak is like not that enhanced. So what property one says that the patterns are essentially smaller than the whole image. The property number two says that the convolution operator, it has got its relevance in identifying the patterns even if the patterns are moving. So that means in the first image of a bird, the beak is actually at the center of the image. But if I take a bird which is picture of a bird which is furthest, maybe the beak would be like in the lower half of the image. The same pattern may be present but at the different region of the image. And the third property is the property from the max pool, which means the subsampling of the images or the pixel will not change the object, because max pool essentially takes out the important carry forward the important properties of a given image. So just to quickly say, if this is a 6x6 image, if I try to take this filter and I convolve this filter onto the given image, what we try to do is we take every pixel that is there in this particular image, we try to multiply with the filter value, plus we take 0, multiply with the filter value -1, we add it, and once we do this we get a value 3. And then we define the stride, which basically says the jump of the pixel. So over here, if we are jumping by 2 pixel, again the concentration is on a new 3x3 image, 3x3 region. And if we convolve this filter on this 3x3 region, let's say that we are getting -3. So if we do this across this complete image, maybe we get the value that is shown where my mouse is hovering, and we can see that there is a value 3, and this value 3 is basically obtained from this patch of the image and another patch, and we can see that both these patch essentially contains the similar value. So this is a clue that when we have identical value, it might indicate that the patches are similar, so which is an indicator that the same pattern can be present at different region of a given image. So every filter would extract different types of different properties of a given image. Maybe the first filter may be the horizontal edge, the second filter may be the vertical edge, and so on. So when we convolve different filters through the same image, we get different outputs, which are essentially called as a feature map. So now what we try to do is, from each feature map, we will take the max pool, which will try to generate a new image. So after every max pool, we get a sub image because the maximum information is retained. Okay, and finally this image is flattened for the prediction. So something like this. So what we do is, what happens in the flattening operation is, let us imagine like we have like a 4 cross 4 as an output from the first activation map. So if we try to arrange them like one after the other, so this arrangement in a 1D representation is called as flattening, which is given to the fully connected layer, which is a feed forward layer for classification. So we made use of some classifiers. So quickly to speak about, like we used in this work ResNet, so which is also called as residual network. And why it is important, we think that as the number of layers in a deep neural network model is increased, in theory we feel that that the training error should be minimized or accuracy should be increased. But in reality, what happens is, as the number of layer is increased, the training error starts decreasing or the accuracy increase. But after some time, what will happen? The error starts to increase. The reason we will talk about quickly. So this has been also studied in the paper by Kekem He, which says deep residual learning for image recognition, which appeared in conference on computer vision and pattern recognition, like CVPR. So if you look at the first diagram, so it says that as the number of iterations are increased, the training error for a model which is trained, which contains 20 layers, it keeps on decreasing. So the same pattern is also observed for still a deeper network, where initially the error was high, but gradually it starts decreasing. So the identical trend is also obtained with the test set. So if we look at the collection of test sample which was given to a deep neural network model trained with 20 layers. So initially it was higher and then it gradually decreases, and this happens with also a 56 layer neural network. So if we observe both the patterns, the trends in both training and as well as the test file is basically identical. So this is not a case of overfitting, because what is happening here is the training error and test error both are increasing as the number of layer keeps on increasing. On the contrary, what overfitting means is the training error decreases, but the test error start increasing, or the test accuracy keeps on increasing. So that means there is no effective generalization. So in order to solve these issues, so we have something called as some architectures called as ResNet or dense net. What they try to do, they perform some sort of a skip connection, and the overall idea is to take the input and forward it, to copy it or forward it into the deeper network. So let's say if the input is X and we have a convolution layer followed by an ReLU activation, and then we have a convolution layer. Before the next ReLU, what we try to do is we try to copy this input over here, so that the effect of this input which was lost for the deeper layer is not minimized. So don't get intimidated by this. So in general, what happens is when we have a given deep neural network model, so the model always tries to compute the loss, which is the difference between the prediction as well as the actual value, based on the different types of loss functions that we are using, plus the regularization parameter, which is represented on the second part of this equation. So what is interesting to find out is, like, when we have a loss, essentially we would like to minimize the loss. So we would try to basically find out the derivative of a given loss function with respect to the parameters of the neural network, which is weight and biases. So imagine that we have found out the loss. So we try to update the parameter, which is represented by W superscript of L, which is equals to W super old weight minus the learning rate, and some value that we get from back propagation, which I am not showing over here, plus the regularization parameter. So next, what we try to do is we take this alpha and we will multiply this alpha throughout this equation and do some sort of a rearrangement. So if we take alpha and multiply with this equation, we will get alpha times lambda divided by m multiplied by W superscript of L minus alpha and something we get from the back propagation. And then if we take W superscript of L common from here, we get the equation something like 1 minus alpha multiplied by lambda divided by m multiplied by W superscript of N. So this is something very interesting to understand now. That is, if the value of lambda, this regularization parameter, is larger, then what will happen? This equation, this sub-expression will be close to 0. So when this sub-expression is close to 0, what it means that in the backward propagation, the parameter values are getting decayed, and our network, which should learn non-linearity, is now transforming to a linear network. So this means weight decay. So which means that the deeper networks, in the deeper network, some neurons will be shut down. So which means that only the information will flow from this region because the backpropagation is not happening appropriately due to large L. So if the value of lambda is large, then W is small. So if W is small, then Z, which is the excitation value that we get due to the product of weight multiplied by the activation plus the bias, will be relatively small. So the activations of the neuron will be roughly linear. So the deep neural network will actually behave more or less like a linear layer. So how do we avoid it? So if we have for W, which is basically equals to 0, what will happen? The information will flow in the forward direction, but we will have no path that is available in the backward direction, because the gradient is like it's becoming so small because of this weight decay. So what can be done is that in the subsequent phase, the forward path will also become weak. So in order to avoid this, what we can do is we can copy the value of the X, which is the input, after some blocks of the deeper network. So at least the input is available. So this is the way the ResNet improves the performance. It adds it adds the input in the forward direction by skipping some blocks. So we worked on different combinations of the neural network. So just to read, the first model was 2 convolution pooling plus fully connected layer. And then we had the 12th model, which is like ResNet 50 with fully connected layer. And then we experimented on 2 benchmark data set. One is the Big 2015, consisting of 10,000 plus malware samples, and which is a 9-class problem. And then the 25 malware families in the Mal-AMG data set from Natarajan's group. And then we did both classification and detection, and for that we also downloaded some benign executables, and these executables were attested they were indeed benign by scanning these samples through virus total. And we found that if we use the Gabor-Markov image on the M11th model, the F1 score was close to 99. And also we can see that the grayscale image, grayscale trained model M10 also gives a result which is close to 97. So this was also repeated on the next data set, which is like the MAL-IMG, and we could find the identical trend with the M11 model. We have 99 percentage of result, and the Markov M11 model also we have close to 99.2 as the result. So this is the confusion matrix. So if you look at the diagonal values, so most of the values are closer to 1, so which depicts perfect detection, and with few values close to 95. So this is done for MAL-IMG, and this is also done for BIG 2015, which means that visualization based detectors are indeed useful for classifying a given malware into their respective family. So I will move on to my uh, uh, third work, which is like few shot malware classification approach, which I did with Shubham Kandhar from TU Delft on few shot learning. So to explain what we did, we used a concept of few shot learning, and few shot learning is particularly relevant when we want to solve classification and regression problem when we have small number of samples. So in this particular image, you can see that so we have a support set, and we have a query, and our interest is to find out this query image, what it is close to, whether it is close to this diamond or square or rectangle or the rounded rectangle. So the interest is basically to find out similarity of a query with a given support set. So the size of the support set is very small. It is not as big as the training set. So they are representatives of a particular family of the malware. So as I said, the training set is big because it will have samples from every class. On the contrary, the support set is small, and this support set is basically used in order to guide uh, the classifier for classifying the test samples. So few shot learning is a form of a meta learning, and it is something called as learn to learn, and it is different from the traditional machine learning problem where we try to train a model with a huge amount of data and then predict the unseen sample. But here the interest is to find out from a given support set the similarity of a query with the elements of the support set. So I will try to give you a real use case. Imagine a parent taking a child to a park for the first time. This child is visiting a zoo, and in the zoo, the child observes an animal, but the child doesn't know what is this animal. So the observation of the child, the keen observation of the child, makes it to memorize the artifacts corresponding to, or the corresponding to this particular animal. And then when the child returns in the home, the parent basically tries to show the child with different images, like on the left with the label like cow, hippopotamus, and the elephant. But now when the child sees the image, it will try to understand that it has seen an animal, identical animal in the zoo. So here, what the child is trying to do, the child is trying to find out the similarity of what it has seen in the zoo with what the from the play card, and then eventually trying to understand that this animal is an elephant. So this is called as meta learning, which is called as learn to learn. So the kid could basically learn by himself by reading the card, and here one card is called as one shot. So this is, if we show one example of each animal, so basically it is called as one shot. So the query sample over here is a never seen sample, and it can also come from an unknown class. So few shot learning can be further uh, uh, augmented or transformed into k-way and shot. So k means the total number of classes. So here we can see there are three classes: cow, hippopotamus, and elephant. And shots means number of samples within the class. So in cow you just have one sample, hippopotamus you have one sample. So this is an example of three classes, so three-way, and one shot, one example from each classes. So k-way and n shot also has got some trend that you can see in this diagram. So if the number of classes are lesser, okay, the accuracy of the model will be good. But as the number of classes are increased, what will happen? The classifier performance will be bad, because there will be some overlapping amongst multiple classes. So on the top, if we are solving a three-way three-way classification, it might be good. But as we increase the number of classes, the classifier might try to make mistakes. So this also happens. So in order to increase the performance of k-way and short learning, what we can try to do is we can try to increase the number of examples within the classes. So that is like three examples from each classes, so which is called as increasing the number of example means trying to give the model different experience or different diversity of the given image. So if we increase the number, if the number of examples within the class is lesser, so the accuracy is less. But as we keep on increasing the number of examples within the classes, the accuracy of the classifier will try to increase. So what we try doing is we used a concept called as Siamese neural network. So Siamese neural network is nothing but Siamese twins, which are basically physically connected by in the body at some part, either maybe the head or maybe the chest, and so on. So basically what we tried doing is like we also use Siamese neural network in order to classify unseen malware samples. So before going to the actual use case that we implemented, the Siamese neural network essentially its job is to find out how similar two objects are. So Siamese neural network are trained with large collection of the samples. So basically what happens in Siamese neural network is we start with a convolution neural network, and we give an example to the convolution neural network. On the top you can see a cow, and this learns the features, and these features are then given are then flattened, which are shown over here, and then we give another image to the same network. Okay, so the both the network shares the identical weight, but the input is different, and we will get different output over here. And then what we are trying to understand, we subtract these two vectors in order to learn the differences. So now if we give a different input over here, which was in the lower part, so the difference will be basically higher. So the Siamese neural network essentially tries to learn the differences between the inputs that are given to the model. So in order to train a Siamese neural network, what we have to do is we have to basically create two different subsets. One is the positive example and negative example. And what essentially we mean by saying positive example, positive examples are the examples which comes from the same class. So for example, 2 coming from the same two cow coming from the same class, we give here 1. Two tiger coming from the same class, we label it as 1. On the contrary, one horse and one buffalo, it is like 0, and a hippopotamus and tiger is basically 0. So once this is done, what we try to do is we give the pair of samples from the positive class and the negative class to the deep neural network model, which tries to learn the patterns corresponding to the given image, and then we give it to some dense layer over here, just taking an example, a vector of size 128, and then we try to find out the differences between the two input in order to learn how close these two inputs are in the feature space. So then once it is done, so to make it further simple, so we take these two images from the positive class. From the first network, we learn a representation R1. From the same network, which is having the same weight, we have a different representation R2. And when this representation, difference in representation, is given to the dense layer, so the dense layer would basically classify them into one of the classes. So let's say I'm using a sigmoid function, which is an S-shaped curve, and which is performing some sort of a prediction. And we already have the label corresponding to them, whether they are belonging to the same class or not. So we try to compute a loss, which basically try to find out the difference between actual and the prediction. And then this loss is back propagated. So we can see it is back propagated to the dense layer and then to the convolution layer. And this process is repeated until the network tries to learn the differences between the input. So this is also done for the negative pair. So as you can see, one cow and hippopotamus, and here we would like to have the target being identified as 0, and this in the training process, this is repeated. So what we did, why did we do this? Because as we know that we have novel malware families, and in new malware families, the number of samples are essentially less. So we wanted to solve, we borrowed the concept of Siamese neural network for classifying the malware. So the state-of-art malware visualization techniques essentially perform some sort of a transformation where they transform a given malware file into an image. But by doing so, they also disregard the malware semantics. And next problem that we wanted to solve, there are certain families, example, let's say ransomware or banking Trojan, where there is scarcity of sample, but on the contrary, one of the family might have sufficient sample. But the normal image augmentation techniques like scaling, rotation, they cannot be done on malware visualization task, because they are not the realistic, they don't depict the real world images, but they are some instructions, and the semantics of instructions have to be preserved. And we essentially wanted to recognize unknown malware families. So in this pursuit, we try to create an image, and the image that we created was an RGB image, which is containing 3 channels, which is called as a gem image, which I will talk in the subsequent slides. So gem basically consists of 3 different alphabets. G stands for the grayscale, E stands for entropy, and M stands for Markov. So from a given malware binary, our interest was to create 3 different representation. And as we know how the grayscale images can be created, but we transform this grayscale image in the form of a GLCM matrix with different face. So let us imagine like this is a GLCM image of a given malware file. Then we use the same malware file, and then we tried creating the grayscale, the entropy graph. And I already discussed how an entropy graph is created. This is an example of four malware variants. On the top is two variants belonging to the same malware family, and you can see that there are certain identical patterns preserved at some region of this image. So we created a gem image, which is basically a 256 cross 256 image consisting of three different channels, in which the first channel was a Markov image of a given malware file. The second channel was an entropy graph of a given same file, and the third channel was a grayscale image. And then these three images were fused together, and this comprises our three channels, and this is called as an gem image. And this gem image was used for training to create the support set, and finally for preparing the test set. So we also did an analysis. If we are improving the input space, can a shallow network, not the ones that we have seen in the previous experiment like ResNet, can be used here, and whether it could give an improved or near equivalent performance. So we used a two convolution layer, which is a shallow convolution. We learned we termed it like this, followed by variable number of dense layers. So as you can see here, two fully connected layer, and with output that is equivalent to the total number of classes. And then we created a Siamese convolution neural network, which is basically having the two convolutions that we saw previously, followed by the two fully connected layer. And then we use the similarity measure, which is Euclidean Euclidean similarity, in order to find out whether the two inputs that were given into two different branches were similar or not. So how the training happens? How the prediction happens? Essentially, you have some, after training, you take some representative samples from each family. So let us assume that there is a family A, family B, and family C, which is shown by three different images where my mouse is hovering. And then we have a query image from an unknown malware family. So what we try to do each time is, like, we prepare the gem image for the malware families A, B, and C, and the query image, and then we will give pair of these two images to two different branches of our Siamese convolution neural network with the class labels as A, B, and C. So every time we will pass two images, and the whole job of the Siamese convolution neural network is to basically find out the similarity. And as you can see that there is a high value of 0.95, so which means that our unseen sample is closer to family number B. So in this example, in this study, we took three data sets. So one is a MAL-IMG data set, which consists of 25 different families. Uh, uh, and we combined two families, which is Switzer as proposed by Natarajan et al., and then Microsoft Big 2015, comprising of 10,000 sample. And we also curated some samples from Malware Bazaar, basically 14 malware families comprising of 8,076 samples. And then by using the gem image, if we also by using different image, we found out the results. So as you can see, if you use grayscale image, we get a result that is close to 9 when we use the grayscale images of MAL-IMG, Big 2015, or Malware Bazaar. And then here is the result of Markov image, entropy graph, gray level co-occurrence matrix, And when we use the 3-channel gem image that we propose, the results for Mala MG dataset is close to 1, and the malware bazaar and big 2050 is also close to 99. So we did two types of analysis. One is the conventional malware classification, where the families in the training set and the families in the test set are identical. And also we did novel class classification, where the families in the training set is basically a subset of the families in the test set. So we have some new samples also in the test set. So for the conventional classification if we compare the results of the with the state of the art, like our results are more or less close to the baseline. But if we also do an analysis of novel class classification, so the state of art techniques, they don't perform well in identifying novel class. On the contrary, the Siamese convolution neural network trained on the gem image, they were relatively better. So last few slides on explainability. So we have a network which has been taken as black box. Now we would like to understand what actually is learned from this images. So essentially we could use a class activation map, which I would talk for another 5 to 10 minutes. But in our recent study with Matteo in the paper that we published in GISA, we also worked on something called as high resolution class activation maps, which could give more focused regions of bytes from the given malware file. So just to explain, what are we trying to answer now through class activation map is what does the network learn. So given an input image on the left hand side, which is an image of a wolf, we have some convolution layer which is performing certain feature extraction, and then we have the gap layer, which is basically the global average pooling layer. So how we can prepare a class activation map? In the first step, what we try to do is we will apply the global average pooling to each feature map. So as I said, when we use different filters, we get a different feature map as an output. So from every feature map, what we try to do, we will try to perform a average. So for example, let's say if I'm having like 4 feature map, so if this is the first feature map, I take the first feature map, I add all the activation values and I divide by the total number of pixel, so which will be the global average pooling value for the first feature map. So if we have 4 feature map, we will be having 4 different values. So imagine like if we are having if from the convolution operation we are having n different feature map, and if it is passed to the gap layer, what we'll get essentially is from every feature map we will get individual value, which is an average value of the feature map. Okay, then what we try to do is now we go to the prediction layer. So what we try to do next step is to learn n linear models from this gap output. So that means for n different classes, we will be trying to learn n different weights. So if you are having n different classes, so from the gap output, we will be learning n different weights. So essentially what we are trying to do is we are trying to learn n different linear models. So once we have n different weights for n different classes, so basically we will be having weight 1 multiply by the feature map plus weight 2 and so on. So what we will be what we will get is like we will be getting the weighted class activation maps, and for different so different weight combinations will be there for the same set of feature maps for different classes. So eventually, what we are trying to do, just to explain you through this example, which is like take borrowed from one of the available literatures, like you have an input, then you have certain features that are extracted, then you have the activation maps. This activation map then is averaged. Each activation map is average. You get different average value. Then you try to learn this weight, and once you try to learn this weight, you know the activations for each of the feature map, and eventually it will give you some region, something like this, our warmer region, which essentially shows the interesting pattern the classifier is learning. And over here it is like the pattern of the dog. So so this is the mathematical equation. So we have Aij, that is the pixel locations in the kth feature map, by divided by Z is the total number of feature map, and Wk is the weight, and this is basically the activation score. So just to explain you, like for example, in this slide, we are trying to plot three different variants of a Gathak family. So you can see that the classifier focuses on this particular region in order to classify a given variant into Gathak family. And if we look at Kalios 1, so the block in row number 2, block in row number 4, and the last block. So you can see that every malware variant, the focus of the classifier is distinct, but for different family is distinct. But within the same family, if you look at the variants, so you can see the concentration of the warmer region that is learned by the classifier is more or less similar. So we also plotted the cumulative class activation maps for each family. So you can see that the cumulative class activation map for agent family is dissimilar from the class activation maps for Kalios, robots, or WA bot. So this is basically an interpretable model, because by this we can clearly explain that the concentration or the focus of the classifier for different malware families are distinct. So this way we can explain, since the warmer regions are distinct, the classifier concentrates on a specific region. So last but not the least, once we appreciate, like we have a malware model that gives exceptional performance, and it could be explained properly, can we perform an adversarial attack on this? So one of the prominent approach was Malgan. So before going into a quick recap of this, so basically is what is security by design now is like we always prepare any machine learning or deep learning model without the presence of an adversary. So the adversary adversarial attack is never kept into consideration. And the second thing is, we always assume that the training set and the test set comes from identical distribution, which is not similar. And the data source that we collect, they does not depend on the classifier. So we cannot say that for eBay CNN is good, or ResNet or SVM is good, and so on. And likewise, we forget that the source does not come with the noise. So there will be a random noise that is also available. So this is one of the wonderful papers to start on adversarial machine learning from the group of Christian Sedeki and Batista Vigo, where the whole idea is like, if I show the picture of a bus on the left hand side and on the right hand side, for a human being it appears still as a bus, but when it is added with some random noise, and it is given to a deep learning model. The deep learning model wrongly labels it as an ostrich. And this example that you see on the right hand side, which is superimposed with the noise, is an adversarial noise. So what is an adversarial example? Adversarial example is a minor perturbation that is added to a given input so that the classifier wrongly identifies it or it labels it into some other classes. So we have different
यहाँ पे
algorithms
तो ऑलरेडी एक चल रहा है.
for the adversarial examples. So like fast gradient sine method and Carnegie uh, CLR method, and many techniques are there. So what are adversarial examples? These are inputs that are that are actually added with small perturbation, which is barely identifiable by human beings, but they are misguided by the classifier. So with this, we have three types of the attack models. So threat models. So one model is called as the white box, where the attacker has got the knowledge of the training data, its representation, as well as the classification algorithm. So this is an upper bound on of an attack. Basically, this is done in order to evaluate whether the model that we want to deploy is robust or not. On the contrary, we have a limited knowledge attack, which is called as a gray box attack, where the attacker is not having an access of training data set, but knows how the features are represented or classification, has a knowledge of the classification algorithm. But besides this, the attacker has got an access of surrogate data, maybe a data he can actually download from the public repository. But the strongest attack model is called as a black box attack, where the attacker doesn't have the knowledge of the feature, doesn't have the knowledge of the training set and the internals of the model. So which means that if you look at the image on the right hand side, the knowledge of the attacker in case of the black box attack is black box model is low, threat model is low. On the contrary, as we move towards the right, the attacker would have more knowledge and he can deceive the system. So with this, we created one adversarial attack on Android malware classifier using generative adversarial network. Also, a black box attack also on the portable executable. So, which I will quickly say, like there is competing network, that is a generator and a discriminator. Basically, they are competing with each other, and their competition is essentially to develop a sample, a functionally preserving malware sample, which could deceive different classifiers. So we don't know like whether the malware classifier are built through random forest or support vector machine or XGBoost. We want to generate an attack which is transferable across all these models. So first, what we try to do is we start with a malware sample, and we try to add some Gaussian noise which has been created through this model, which we superimpose. And the only assumption is like we can do as many queries to this black box model. So what we try to do is we get the superimposed data which we give it to this black box detector, and this black box detector will actually give us a label. So what we try to do, already the discriminator has been trained with a collection of malware as well as the legitimate program. So the discriminator will try to, it acts as a surrogate model. It tries to learn through the patterns of the labels that is outputted from this black box. So at the same time, what the generator observes is the loss of the discriminator. So if the discriminator still identifies the samples appropriately, what happens is this: we try to add more noise to the given input. Eventually, a time will come where the discriminator loss will be higher. And then at that point of time, what we try to do is we will use that distribution and keep on generating more samples, and those samples will be basically fooling this black box detector. So this is what we tried doing it. But in this concept, one important thing we have to do, we have to keep in our mind is like whenever there is a feature that is already present in the malware sample, we cannot make it zero. Otherwise, the functionality of the sample, malware sample, will be corrupted. So as you can see in this picture, like the second cell over here, it was one. So something that is one is retained as one, but something that is zero can be made as one. So here, like if it was zero, we make it one, but something that is one will be retained as one. So for example, the third one will be retained as one, but the fourth one, here we are doing some feature augmentation. So this process is training process is repeated, and this discriminator, which acts as a surrogate model, will be trained on the output of these labels. And as soon as the error increases, what happens, the generator will try to generate those samples in order to fool the black box model. So with this, I would try to stop my lecture, and I'm open to any questions. And presently, we are working on basically trying to create personalized malware detection model through the concept of mixture of expert. Also, we are trying to deploy black box. We are trying to deploy certain backdoor attacks on malware detectors. And the third problem that I'm working with a couple of my students is, can we try to create privacy preserving anti-malware, because since malware detectors are particularly running in the super user privilege, so we might feel that it might breach privacy. So we are using federated learning concept with differential privacy in order to prepare a privacy preserving anti-malware system. So with this, I would like to close, and I'm open to any questions you have.
Thank you so much, sir, for this insightful session. So, participants, we are now open for this question answer session. So, if you have any question, you may put it in the chat box.
If you have a question, I would be really happy to address. Also, I leave my email address if you are uh, interested to know what we are doing, or if you are interested to, if you are interested for some collaborations on malware detection, or uh, let's say security of AI that we are exploring now in our lab, I would be really happy to discuss with you all.
So, I hope there are. So, sir, actually, I think it was self-explanatory. The way you have explained, I think it was clear, and definitely it was a kind of session where you have shown the path to the participants how they can explore it in a different AI perspective, how they can explore the malware analysis in perspective of AI models, and what are those possible research areas that they can explore. So this was literally a kind of a very insightful session, and we are very much thankful for taking out time and having this insightful session on our FTP. So thank you so much, sir.
Thank you,
I
sir,
hope
for
We,
giving the
we will
opportunity.
see
Thank you.
you. Yes, definitely we will have some more session on this one on malware analysis in future. So on behalf of organizing committee as well as the participants who have joined, I would like to again thanks for this insightful session. Thank you so much, sir.